All right, Calc 3, welcome in. It's Tuesday, August 24th, and we are starting week 2. And we are also going to finish 11.2 today. I have parallel vectors I want to talk about, and then an example using parallel vectors. That'll finish 11.2. And then we will cover 11.3, which introduces a multiplication for two vectors known as the dot product. Super useful for physics, super useful for finding out physical things about two or more vectors, yeah? And so we're going to define a multiplication of two vectors that's super useful, yeah? Let's get started. So, last time I may or may not have, I'm trying to remember, but I might have given the definition of a parallel vector. I think I did because I talked about parallel and skew lines, but now I want to talk about parallel vectors. Simply put, two vectors are parallel if they're scalar multiples of one another. So it really is that easy, right? So our definition of parallel just says this: two non-zero vectors are parallel if there is some scalar between them, right? Such that the one vector u is some c times the other vector v. Okay, so if you can find that c, then you know they're parallel vectors. So for example, let's take a look here. Suppose I throw the vector 3, -4, -1 at you, like this. Okay, and so you have this three-dimensional vector, 3, -4, -1. And now I want to ask, is the following parallel to another vector, right? So let's say that w here, let's say that w is -6, 8, 2. Okay. Now looking at these two vectors, their component forms, you can tell right away the answer to the question if these are parallel or not. So are u and w parallel? Right? And how can you tell? Well, if you say yes, then you need to provide the constant, the scalar multiple between them, right? So for instance, I noticed that if I take 3 and I multiply it by -2, I get -6. If I multiply that by -2, I get +8. And if I multiply that by -2, I get +2. So it looks like if I take u and I multiply it by -2, I get w. And so therefore, u and w are parallel. So the answer is yes. Note that -2 times u equals w. And so the constant, the scalar between them is -2, right? You could also say this, right? You could have also concluded that w is -1/2 u. That would also tell you that they're parallel. Either one of those statements is good enough to conclude that they're parallel. The point being, I don't have to graph these. I don't have to get GeoGebra out and look at them and say, yep, they look parallel. This is just a very nice, easy way of determining if two vectors are pointing parallel, right? Now remember, informally, parallel means that they're either pointing in the same direction or 180 degrees from each other, right, as well. And so those would both be counted as parallel. Awesome. So those two vectors are parallel. And for instance, if I gave you another vector like this, what if v was 12, -16, and 4, like that? Okay. Let's see here. If I multiply 3 by 4, I get 12. So I'm thinking 4. -4 times 4 is -16. -1 times 4 is -4, but this is +4. So therefore, 4 does not work. But 4 was the only possible thing that it could have been. The only thing I can conclude now is that u and v are not parallel. U and v are not parallel, right? Because to make the x coordinate work, right, the I component work here, I need to multiply by 4. And so this needs to be multiplied by 4 and this needs to be multiplied by 4, but it's not correct for all three components. And so therefore, these vectors are not parallel. Yeah. All right, cool. So that's a quick way of determining if vectors are parallel. Let's get to now our final example, 11.2. And here's kind of a nice little problem that gets you thinking a little bit of geometry as well, right? Suppose I throw 3 points at you, not vectors, but points, all right? Now, you might remember from geometry, if I throw 2 points at you, you could always draw a line between them. There's a straight line that contains both of those points, yeah? No matter what 2 points I give you, well, as long as they're different points, yeah? But now if I throw a 3rd point at you, say this one, and this one up here, now it may be the case that one line goes through all 3, but it's possible, in fact highly likely, that one line does not go through all 3, right? And so it actually makes sense to ask the question, hey, I have 3 points here. Are these collinear? Do they live on the same straight line? So we're asking here, determine whether the points P1, -2, 3, Q, which is 2, 1, 0, and R, which is 4, 7, -6, are collinear. In other words, they cohabitate on the same line, right? They live on the same line, collinear, yeah? Now, this might be a tough question if we didn't have the proper tools for it, right? Because let's think about this, right? It's like I throw a point at you and I throw a second point at you. And now it's like, well, okay, a 3rd point enters. How can I tell if it's here and actually on the same line, or if it's like up here and now I don't have a single straight line that goes through all 3? How can I tell if it's here, if the point is like here, or if it's here, right? And since it's 3D, it's even harder to sort of draw that out and see the perspective on it, right? This is where vectors are going to be very nice to work with, right? So think about this. What if I have this one point as P, and this point is R, and this point is Q, right? And let's say they weren't parallel. If they weren't collinear, right? Notice what happens when I form the vector PQ and then form the vector PR, right? Notice that these two vectors are not parallel, right? This has to point off of the line to Q, and this has to point to R, definitely seeing that these vectors are not parallel. Okay, they are not pointing in the same direction or opposite each other, right? Now, if Q was on the straight line, the same line, do you notice that the vector PQ now, if Q was moved down here, do you notice that PQ would then be parallel to PR? Do you see that? They are just a scale of one another. This is whatever times this length here, yeah? So the question of whether these 3 points are collinear can be very easily answered by forming PQ, the vector PQ, and forming the vector PR and asking if they are parallel vectors. If they're parallel vectors, the 3 points are collinear. If these are not parallel vectors, then the 3 points are not collinear. Yeah, seem reasonable? Let's go ahead and execute that plan. So I'm going to form PQ. PQ is the vector, so this is the initial point. This is the terminal point. So I'm going to do terminal minus initial, so 2 minus 1, comma, 1 minus a minus 2, just 3, 0 minus 3, just -3. I'm going to form PR, which again, terminal minus initial, 4 minus 1, 3, 7 minus a minus 2, 9, -6 minus 3, -9. And now I ask the question, is PQ, the vector PQ, parallel? Can I spell parallel? Parallel to PR. So now all that matters is finding a multiple, if there exists one. So to get the x coordinates to match up, I would need to multiply by 3, wouldn't I? 3 times this would make the x correct. So then I just have to make sure, does 3 work for the others? 3 times 3 is 9, perfect. 3 times negative 3 is negative 9. Perfect. My multiple is 3. These vectors are parallel. Therefore, the points P, Q, and R are collinear. So yes, PQ, in fact, if I take 3 times PQ, I get PR. Yeah? And so therefore, they are parallel. Therefore, P, Q, and R are indeed collinear. They must live on the same line because the vectors formed are parallel. So there's that one-to-one connection between parallel vectors and collinearity. Okay? Awesome. All right. That's cool. That finishes 11.2 for us. So there's a bunch to practice there. So if you haven't done the homework in 11.2, boy, get to it. You need to you need some practice on the basic stuff. Even if you think it's easy, which I do hear a lot of students say, oh, this is easy, I don't need the practice. Yeah, you kind of do. You want to make sure that there's some things also in the homework that I didn't quite mention that you have to think through a little bit, right? So you want to make sure that you go a little bit further beyond just knowing the basics, right? You want to be able to apply that and practice that skill. These are fundamental skills to what we want to do in the future, right? So knowing your basic vector math is so important for applications later on down the line, especially if you're in like a physics class or an engineering class where vectors are all over the place, right? So you want to make sure that you are really knowing that stuff really well. And the only way that that happens is by practice, practice, practice. Yeah? Awesome. Let's now introduce a new operation between two vectors. And this one's a multiplication of in a certain sense, called the dot product. Right? So we know how to add two vectors, we know how to subtract two vectors, and we know how to scalar multiply a scalar times a vector. So now this is our first experience, at least in this class, with a vector, quote unquote, times another vector. I want to sort of invent a multiplication. And a multiplication of vectors, I want it to make sense. In other words, I want it to be useful in a physical way, right? So at first, this definition is going to look pretty arbitrary and pretty like, well, that's just a fun math thing you could do. Why did you do that? Well, the answer is because when it's defined that way, it does certain useful physical things, right? And so we're going to start with a definition. It's probably going to look like, okay, sure, you can do that calculation. I don't know what that does because the definition alone doesn't really tell you what it does. You'll be glad to know it's easy to calculate for sure. But then once we get the definition down, we'll get into why it's defined that way, because we'll start seeing the usefulness and you'll start seeing it show up everywhere, right? So the first thing we want to do is define what we mean by a dot product. So let's start at the very beginning by doing a definition. Okay, let's say we want the dot product of U, which let's do a two-dimensional, U1, U2, and V, okay, V1, V2. Okay. That's going to be a mouthful to say all the time. So instead of saying the dot product of U and V, I can use this symbol, U dot V. Okay. And I need to say dot product, by the way, because, spoiler alert, we're going to have two different multiplications for vectors. I said it. This is very different than real numbers, right? When I say, what's 3 times 5, you don't ever respond with, oh, what multiplication are you talking about? Right? You just do 3 times 5. You're like, 15. Okay, repeated addition. That's, of course, what you mean when I say 3 times 5. There isn't another choice, really, right? But with vectors, there's actually a choice of multiplication. There's two very, very popular multiplications that do two very different things, and they're both quite useful. And so we actually have two very useful multiplications. When you take linear algebra, right, you'll find out there's an infinite number of multiplications for a mathematician to play with these vectors here, and you can invent all sorts of multiplications. Whoa, what? Multiplications? Plural? Yes, indeed. Yeah. So there's many multiplications one could do. You're being taught two very popular ones because they tie in with physics and engineering so well. So enough talk. What's the definition of a dot product? U dot V is going to be a scalar. It's going to be a number, not a vector. And it's going to be this certain number. Take the components and multiply. U1 times V1. Add to that U2 times V2. That's by definition what the dot product of two two-dimensional vectors is. The dot product of U and V is the components multiplied and then the sum of those. So the sum of the components multiplied. That's a really good way to think about it, because if I had, so the dot product of U equaling, what if it was now U1, U2, U3, right? Like that. It was a three-dimensional vector, and V was V1, V2, V3. The dot product would extend, I hope naturally, what you would think it would do. You still take the sum of the multiplication of the components. So you're going to do U1 times V1 plus U2 times V2 plus U3 times V3. Right? So just at a basic mechanics level, notice that the input of the dot product takes two vectors. You plug in two vectors, you multiply them together, you perform this operation, and out spits a real number. You see that? So it takes input of two vectors and outputs a single value. Okay? And that value is a scalar, right? So note the dot product gives a scalar, not a vector. Right? So U dot V equals a quantity. Okay. Now, why do we might call this multiplication? Isn't that a little presumptive? It's a little bit like, why call that multiplication? Right? Because yes, it involves multiplication of numbers, but we're adding as well. So why would it be called a multiplication when there's like addition involved in it as well? Well, the answer to that lies in knowing the properties of the dot product. The dot product acts like we want multiplication to act like. Now, what the heck does that mean? Have you ever thought about having an option or having an ability to say, this is what I want multiplication to do? Right? That doesn't seem to be usually your call. You're usually just told by a math teacher, this is what multiplication is. Just do it. Right? And it works this way. You don't necessarily get to be in the driver's seat and say, okay, what should multiplication do? We don't ask the should question very often. It's just, what is it, right? But there are certain properties that we want multiplication to follow, right? If you sort of think about it a little bit, yeah? One of the nice properties that not all multiplications follow, but most do, is commutative. 3 times 5 is the same thing as 5 times 3. And so, excuse me. Ooh, had a little cough there. Just something in my throat. Okay. So, about commutativity, I want to ask the question, is it the same thing if I do U dot V? Is that the same thing as V dot U? So U dot V, is that the same as V dot U? Well, what do you think? When you look at the definition of U dot V, it's the components of U times the components of V, and then added together. V dot U would literally be the swap of this, which would mean it was V1 U1 plus V2 U2. And you see, those would be identical, wouldn't they? Because U1 V1 is regular, good old-fashioned real number multiplication, right? And so U1 times V1 is V1 times U1. So U dot V is commutative. You can swap it because you can swap regular, good old-fashioned multiplication. You see that? And so we do indeed get this property. that we get commutativity, which is a nice thing for multiplication to have. It's commutative. You can go back and forth, just like your commute from work and back again, you can commute. Multiplication. Another property that we like multiplication to have is that it's distributive. And so what would happen if I take u dot vector v plus w? Well, in a perfect world, if I had my choice for multiplication, I would love to be able to distribute this like it was multiplication of real numbers, like in algebra class. And guess what? The way that it's defined, I do get that property. So it acts like the multiplication that I want. This is yet another thing I want multiplication to do. Distribute over addition. U dot v plus u dot w. That's the same thing as if you did u dot v plus w. This is called a distributive property. And that's what real number multiplication does, right? That little thing in front distributes to both terms, right? So does the dot product, right? Now, I haven't proven that. You can prove that very easily by just calculating this and then calculating that, yeah? Okay, then another example here, another property. What if I take C and I multiply by u dot v? Okay. Now u dot v is a number, right? Because u dot v is a scalar. So this is some number times the number c. Okay. What's nice to know here is that this is the same thing as had you done scaled u and then dot that with v. Or it's the same thing if you scaled v first, then dotted. Any way you slice it, these three things give the same result. This is called an associative property. Associative property. Which means you can reassociate the parentheses. So you have the three objects here, the c, the u, and the v. You can move the parentheses like this and you're still good. So you can do cu dot v, or you can move the parentheses like this and be good, or you can move the c in and then associate parentheses and you're still good. This is what we want regular multiplication to do, right? That's what regular multiplication does. It's commutative, it's distributive, it's associative, and that's exactly what dot product is as well. So this is getting you some insight as to why we might call this a product, because it acts like multiplication does. In fact, here's another example. What would happen if I multiplied a number by 0? Well, I would get 0. So you might ask, well, what happens if I dot a vector with the 0 vector? Well, let's see what happens. Right, if one of these vectors is the 0 vector, I'm working with 0, comma 0. Well, that's going to be 0 times whatever plus 0 times whatever. Notice what I would get. U dot v, 0 dot v would be 0. So 0 dot v is the number 0. That's a property of multiplication, isn't it? When I multiply something by 0, I should get 0. And even though this is two different worlds, this is a vector, 0 vector dotted with a vector v, I get the quantity scalar 0. So it acts like multiplication. All right, now the last property in this list is an important one, and we will reference this one quite a bit. When I multiply a vector by itself, right? For instance, if I multiply a number by itself, I get it squared, right? X squared, right? So 3 times 3, 9, right? I get its square, right? When I dot a vector with itself, this ends up giving me the magnitude of the vector squared. And this is a very important property that we will use often in this class. Isn't that kind of nice? When I dot product a vector with itself, the number that I get after doing that is the magnitude of that vector squared. Let's actually prove this one. This one is not bad at all. So I'm going to prove the two-dimensional version of it, and the same exact argument works for 3 dimensions. So prove v dot v is equal to the magnitude of v squared. Okay. To do this, I'm going to let v equal v1, v2. Okay. Any generic two-dimensional vector you like. I'm going to calculate the left-hand side, LHS. Left-hand side is v dot v. So let's go ahead and calculate that. V dot v means I multiply the vector component of the first one times the vector component of the second one. So since it's v, it's going to be v1 times v1. So I get v1 squared plus v2 times v2, which is v2 squared. So the left-hand side, I get that. Okay. The right-hand side, I get the magnitude of v squared. Let's do the magnitude of v and then square it. So the magnitude of v is the square root of v1 squared plus v2 squared. And then I want to square that. Well, of course, squaring the square root undoes one another, and I end up getting v1 squared plus v2 squared, and these are in fact identical, aren't they? The left-hand side is identical to the right-hand side, and so there we've proven it. We now have the fact that when I dot a vector with itself, I get the magnitude of that vector squared, right? So that means I have an alternative formula, by the way, for the magnitude of a vector. If I wanted to, I could find the vector, the magnitude of the vector, to be the square root of the vector dotted with itself. Is that useful? Not usually, because you're doing the same exact calculation as always. But it is maybe theoretically useful. It's nice to have another description of the magnitude involving the dot product, right? So this doesn't really help calculation-wise because it's doing the same calculation. But, you know, maybe for some theoretical concerns, that might be nice to remember that there's that connection between the magnitude of a vector and its dot product. Okay, very cool. Any questions from the live group here on what I'm doing so far? We doing okay? Thumbs up if we're doing okay in chat there. Be sure to like and subscribe. No, just kidding. Hey, those of you in Zoom, are you okay? Thumbs up.
All good.
All right. Thumbs up, all good. Okay, okay. Nice. All right, excellent. Now, let's get to more things that the dot product does, right? Right now, it looks like it's just a fun calculation. Like, okay, randomly multiply the components together and then add them. So what, right? Why not multiply the components and then multiply by 7 randomly and then add 3 times the other components, right? I mean, that seems just as arbitrary as what I've just doing. Well, let's get into why it's defined the way it is and what sort of things that we can do with that dot product. And the first thing I want to talk about is the dot product is going to allow us to find out the angle between two vectors. And that's one of its primary jobs, is to really start to get an idea of how one vector relates to another vector as far as their angle from one another. So first, let's define what I mean by the angle between two vectors. So the angle between two vectors, and even the use of the word the, that's sort of suggesting that there's only one choice. The angle between two non-zero vectors. Okay, let's call that theta. And right away, I'm going to make a restriction. Theta can't be anything it wants to be. I'm going to force it to be between 0 and pi radians. Okay. The angle between two non-zero vectors, right? So I have a vector v, let's say, and I have a vector u, let's say. Okay. Theta is going to be this angle measurement between those two directed line segments. Okay. And notice that it's going to be either an acute angle or an obtuse angle, right? For instance, right, I would say that the angle between these two vectors is theta and not this ridiculous angle here, which would start here and go all the way around this way and come around like that. No, 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 right? There seems to be two options maybe, right? There seems to be this option here and this like option that starts here and goes around the other way. But that's not what I'm talking about when I say the angle between two non-zero vectors, right? And so even if this was an obtuse angle like this, vector v here and vector u here, like this, right? This is the theta I'm talking about and not this one here. You see that? And so even if this was to sweep out and go past 180, well, then I would just pick up the angle on the other side, right? And so this makes sense to talk about the angle between two non-zero vectors if I limit it to between 0 and 180 degrees, or rather 0 and pi radians, okay? So first off, that's what I mean by that. And notice that, you know, that's the same whether it's in a piece of paper, two-dimensional, or if it's three-dimensional, right? I mean, I could have a vector here, right? So I could have a vector here, and I can have a vector, you know, like this, like that, right? And they form some angle, right? And in fact, that angle is being constant, even though this might be an object that's rotating. Do you see that? The angle between these two vectors is staying the same, right? Now, by the way, they don't have to be connected to talk about the angle between these two vectors. This angle between two vectors is the same whether they were drawn like this or if they're drawn like that. Remember, vectors can be picked up and moved as long as they're not, you know, rotated and as long as they're not scaled, right? And so, yeah, so this is the same angle between these two vectors as this is. Doesn't matter where they're positioned. Of course, oftentimes in the applications, I'm going to pick this one up and move it so it looks like this, so then I can talk and easily see the angle between those two, right? But remember, in application, I don't need them to be touching. They don't matter. It doesn't matter for vectors where they're at. They'll have the same angle between them whether their initial points are touching or not. Yeah? Okay, now that we know about the angle between two non-zero vectors, let's get to a super important formula. And in fact, this formula might be the way that a dot product was defined in your physics class. Sometimes physics books like to define it this way that I'm going to do, and then derive our definition. This math book likes to start with the definition that we started with and then prove that the next formula that I'm going to write works. Either way, they're both equivalent. So there's two equivalent definitions of the dot product. One is super useful for physical problems, and the other one is really useful for math theoretical problems. Yeah? And so let's get into a formula that tells me how to find the angle between these two vectors. And here it is. Here's the following formula. We get that the cosine of this angle of theta, where theta is the angle between the two vectors, is actually equal to the dot product of u and v divided by the magnitude of u times the magnitude of v. Okay? Super important formula right there. Right? Right away, I'll write an alternative formula here. You can solve this for the dot product, just like I said, and now you would have that the dot product of these two vectors is also equal to the magnitude of the first vector, u, times the magnitude of the second vector, v, times cosine of the angle between them. See that? So this is an alternative formula for the dot product. So we have the component version that we can calculate, and that's really useful. Or if you're given a vector not in component form, but in a physics problem where maybe you're given the magnitudes of the vector and maybe that they're like 45 degrees acting with one another, then this is an easier way to calculate the dot product. You don't even have to think about the components. You can just plug in the magnitudes and multiply by the cosine of the angle between them. So this is super useful when we have physical properties of the vector. Yeah? Okay, now as a mathematician, I want to ask the question, and then maybe it's annoying, why? Why does this formula work? There seems to be nothing at all inherent why cosine should show up, right? Would you agree with that? It seems really strange and out of place that cosine shows up in this formula. How? How did we get from u dot v being just u1 times v1 plus u2 times v2 to all of a sudden a cosine showing up, and then that can figure out what that formula is? It's actually really crazy if you think about it, yeah? Well, let me draw a picture that might spark some understanding as to why cosine shows up, okay? So here's two generic vectors. Let's say that we have v like that, and let's say we have u like this, okay? Well, I can always close the third side of the triangle by doing a certain vector. So in fact, if I draw this from here to here, this vector is actually the difference of v and u. Now, can you visualize that? Right? Here's v going out that way. If I take v and add to it the opposite of u, so the opposite of u is pointing up this way, right? Upper left. If I take away u, that means I'm going out v, and then I'm going this way to u, like that, and then forming this vector here. Well, notice, pick up that vector now and move it. It finishes, it completes the triangle. So I can do this with any two vectors. I have an angle between them. I have a vector v and a vector u. That third side of a triangle is v minus u. That is an important picture to understand that. So that difference forms the third side of a triangle where u and v are legs of that triangle, or are sides of that triangle. Now, I don't know if this triangle is a right triangle or not. It might be, it could be, depending on the scenario, but it's most likely not going to be. And so guess what? If I know that this triangle is possibly not a right triangle, there's still a law that connects the three sides together. And would you believe it? The law of cosines does that. And so we have the following statement that must be true. The magnitude of this side, which is the magnitude of v minus u squared, has to equal the magnitude of the one side, so magnitude of u squared, plus the magnitude of v squared, minus 2 times the magnitude of u times the magnitude of v times the cosine of the angle between u and v. This is the law of cosines. This statement must be true, borrowing from trigonometry there. Now, I'm not going to write down all the detail, but I am going to show you the textbook on how this works. Yeah, so let's take a look here, right? And let's zoom in a little bit. Okay, and so we've written out the law of cosines. This must be true, right? Because it forms a triangle, and the magnitudes of the vectors form a triangle, and so they must have this relationship. Well, what they do is further break down the left-hand side. The magnitude of v minus u squared, well, wait a minute, that's a vector's magnitude squared. That connects with the dot product. Remember our rule from before, right? We had that v dot v is the magnitude of v squared. So that means magnitude of v minus u squared is v minus u dotted with itself. So they go ahead and say, this is just this dotted with itself. They use the distribution property. They use the distribution property again to multiply this all out, and I get v dot v minus u dot v minus v dot u plus u dot u. But wait a minute, v dot v is the magnitude of v squared. So they replace it with that. U dot u, right here, is the magnitude of u squared. And since u dot v is equal to v dot u, this doubles up, but negatively. So this is negative 2 u dot v's. Okay, now plug that back in. We now know that's what the left-hand side equals. It actually equals this. So they go ahead and plug it back into the left-hand side, and so now I have this lovely equation. I have this mess equals the right-hand side, which we didn't touch. But now, do you notice that we get cancellations happening? Magnitude of v squared cancels with the magnitude of v squared over here. The magnitude of u squared cancels with the magnitude of u squared over here. So all that survives is negative 2 u dot v equals negative 2 magnitude of u, magnitude of v, cosine of theta. And so now solve for whatever you need. They solve for cosine of theta. So divide both sides by negative 2, magnitude of u, magnitude of v, and that's our formula right there. This is why cosine shows up to the party. Yeah? Because the way that vectors are defined, the way that addition is defined, and the way that subtraction is defined forms three sides of a triangle, and so I can borrow all of the results of trig that apply to triangles to this. And so that's our deep connection to the cosine of the angle between two vectors. Nice. Okay, awesome. Now, this makes the dot product extremely useful if you think about it, yeah? Because now it puts some meaning to the number that we get for the dot product. Check out this picture down here. I was going to move off of it, but I think this is perfect for what I want to do. So let me even blow this up a little bit more. Yeah, there we go. So, knowing that the dot product, let's say, is positive. Okay, let's look over here. So the dot product being positive. Well, using this formula, right? If the dot product is positive, that's a positive number divided by the magnitudes of u and v, which are always positive numbers. So what I can conclude here is if the dot product is positive, that means the cosine of theta is positive. And you might remember from trig class, if the cosine of theta is positive, that means the angle lives in the first quadrant. Cosine is positive in the first quadrant. And so guess what? That means if the dot product is positive, that means cosine of theta is positive, which in fact then means that theta is an acute angle. I know that theta is an acute angle, which is between 0 and 90 degrees. You see that? So just knowing that the dot product of two vectors is positive tells me instantly whether it's an acute angle or not. Right? I can go further than and actually say what that angle measurement is, of course, but it's really nice to just say positive dot product, meaning it's an acute angle between the two vectors. Likewise, if the dot product is negative, if it's a negative number, which that can totally happen, right? Depending on if the components are negative or whatnot. If the dot product is negative, check out what happens with this formula. Now I have a negative number divided by something always positive. So now I know the cosine of theta is a negative number in that case. And because cosine is a negative number, I know it lives in the second quadrant, the angle does. And so that means that the angle has to be somewhere between 90 degrees and 180 degrees. Right? This really gives us a nice way of looking at the dot product. Positive dot product, acute angle. Negative dot product, an obtuse angle. And the special case, what if the dot product was 0? Well, if the dot product is 0, this is 0 divided by not 0. So that means it's 0. Cosine of theta being 0 gives me that the angle has to be 90 degrees. And so the dot product being 0 tells me instantly that the vectors are perpendicular, 90 degrees angle between them. Do you see that? So the dot product, knowing it's 0, immediately allows us to tell if two vectors are perpendicular. We don't usually use the word perpendicular, by the way. We usually use another word that means basically the same thing, and we say that two vectors are orthogonal. Orthogonal. So let's go ahead and write down our rule that we just got from that notice there. So we can say here, the vectors u and v are orthogonal In other words, theta equals 90 degrees, or pi over 2 radians, when u dot v, doesn't matter which order I write, u dot v equals 0. How about that? So we know when vectors are parallel, they're scalar multiples of one another. We also now know when they're perpendicular, or rather orthogonal. That's if their dot product is 0. So we have a nice, really quick check to determine if two vectors are acting normal to one another. That's yet another word we use to describe perpendicular. So there's 3 terms flying around: perpendicular, orthogonal, and normal. They all basically mean the same thing. That basically means meeting at right angles, right? But there are certain contexts in which we use it. Perpendicular is usually reserved for lines. We say that lines are perpendicular, or planes are perpendicular to other things. Vectors we tend to use orthogonal. We'll say that vectors are orthogonal to other things. Or sometimes we say that a vector is normal to a line or plane. Yeah. And so that's, there is a subtle use there that's not hugely important, but you'll notice that the book tries to to be careful between that. So we often say that 2 vectors are orthogonal. We'll say that 2 lines or planes are perpendicular. And then we'll say that a vector is normal to a line or a plane. But if you said 90 degrees or one of those for any of the other cases, people will generally know what you mean. Right? So it's not a huge deal, but there is some vocabulary there. All right. I think it's time to now do some examples. Yeah. We've been talking a little bit theoretical here. Let's now just crank out some basic examples, calculating dot products and finding angles between vectors and all that good stuff. So example time. Let's say that u is the vector 3, negative 1, 2. Let's say that v is the vector negative 4, 0, 2. And let's say that w is the vector 1, negative 1, negative 2. Okay. I'd like to find the angle between u and v. Angle between u and v. All right, to do that, I can use our very nice formula. The cosine of the angle, right? I at least know what the cosine of the angle is going to be. It has to be u dot v divided by the magnitude of u times the magnitude of v. So at least I'm very clear on what I have to calculate here. So let's go to the side here, and I'm going to calculate u dot v. Right? U dot v is going to be 3 times negative 4 plus negative 1 times 0 plus 2 times 2. The result of that gets me negative 12 plus 0 plus 4. So negative 12 plus 4 is negative 8. Now stop right there. Just knowing the dot product is negative I know that my angle is obtuse. These vectors are in some sense acting away from one another. Right? Would you agree with that? So one vector might be doing this, and the other one is doing sort of like that. Right? There's an obtuse angle between them. Yeah. So they're sort of acting apart from one another instead of working like with each other, if you will. Just an informal way of saying that. Yeah. But now I can get more specific. Right? So the dot product is negative 8. Let's go ahead and calculate these magnitudes. The magnitude of u is going to be the square root of 3 squared plus 1 squared plus 2 squared. So that's going to be the square root of 14. The magnitude of v is going to be the square root of 16 plus 0 plus 4. So this is going to be the square root of 20. And so I get this, negative 8 divided by the square root of 14 times the square root of 20. That is definitely not a special angle that I just know off the top of my head, yeah? So obviously it's calculator time to get some sense of what's going on here, right? So to get theta, I am going to use the inverse cosine. the arc cosine. Now, this is super useful, remember, because theta is either the first quadrant or second quadrant. I know it's second quadrant because the dot product is negative. But arc cosine gives answers in the first and second quadrant. So this is one of those rare cases in trig that the calculator will actually give us the correct answer directly. We don't have to do any shenanigans about unit circle. We don't have to think about the third or the fourth quadrant. We don't have to add pi, subtract pi, add 2 pi. None of those concerns come into play in this one application. So yay, right? That's awesome. The calculator will directly tell me what the angle is because of my restriction of theta from being first to second quadrant only. Yeah. So here we go. Let's try this. So clear that out. And what I got going on here is I want to do the inverse cosine, the arc cosine of, now be careful with your parentheses here. -8 divided by, make sure you put this in parentheses, the denominator, square root of 14, right, times the square root of 20. And then end the parentheses. Right? Please make sure that your denominator is in parentheses there. Right? If you don't put parentheses there, it's not going to multiply. It's going to just do -8 divided by root 14, and then it's not going to divide by the root 20. It's going to multiply it by instead. You don't want that. You want it to divide by both of those square roots. So doing that gets me this quantity. Now that might look weird. That is not in degrees. My calculator is in radian mode. And so theta is about 2.0692 radians. Okay? That's useful in math class, but maybe not quite useful for regular life, right? And so it might make a lot of sense to convert this to degrees, right? Especially if you're doing an applied problem, right? So you might want to multiply this by what? 180 over pi. 180 over pi to convert that to degrees. Or in this one case, have your calculator in degree mode where it would tell you that directly, yeah? So I can do it this way. I can say mode and then go to degrees here, like that, and then redo the problem, right? And now it gives it to me in degrees. By the way, an obtuse angle, right? I was expecting that. Greater than 90, but less than 180. So 118 degrees. 118.56 degrees, sure. We don't really care about sig figs in math class. It's whatever. Yeah. Obviously, if you're using in an engineering class or a physics class, please follow the convention in those classes. Right? In math, though, it's like, just round whatever looks good. Don't round too strongly, though. Don't round too harshly. Yeah. All right. Good. Any questions with that? Any questions with that? I would now like to know, what is the angle between U and W? Okay, so let's go ahead and do that example. What is the angle between U and W? Right? Now, once you get really comfortable with your dot product, you'll be able to do those in your head. So I'm looking at this like 3 times 1, which is 3, plus 1, which is 4, minus 4. 4 minus 4 is 0. The dot product of U and W is 0. The angle between these is 90 degrees. U and W are orthogonal. Do you see how quick that was? Once you get real comfortable with that dot product and you see, look, the dot product is 3 times 1, 3, plus 1 times 1, 1. So 3 plus 1 is 4. 4 minus 4 is 0. Bingo. I get that it's orthogonal, right? Obviously, you could use this formula again. You would get 0 divided by the magnitudes there, which would not be 0. And so you'd get 0 divided by not 0, which is 0. And then the arc's cosine of 0 is 90 degrees, or pi over 2. Yeah? Okay, so that is an example for that. Cool. Now, let's get into some other ways that we can measure how vectors, what direction they go in, especially in 3D, right? Now, in 2-dimensional space, a vector, I could tell you that it's pointing in this direction by just telling you sort of its rise over run, right? It has a certain rise and it has a certain run, yeah? But in 3D space, do you notice that rise over run doesn't make as much sense anymore, right? Because, right, the rise might make sense. It goes from this height to this height up here, right, up to here, right? But in what direction does it run? Yeah, there was only one or two directions, I guess, positive and negative direction in 2 space. But in 3 space, run, does it mean run that way? Does it mean run this way? Does it mean run this way? Does it mean run that way? Right? So rise over run become inadequate to describe what direction vectors point in a 3-dimensional space. Yeah? We need an alternative or different way of sort of suggesting that this vector is going that away, right? And so one way we can do that is through something called a direction cosine. So let's talk about our direction cosines. What this is going to do is at least be one way to figure out that this vector is pointing this way, especially with relating it to how it relates to I, J, and K. Okay, so let's get to this. So, direction cosines here. Okay. First, I just like to use a generic vector. And in fact, I'm going to use GeoGebra for this visual. I'm not going to draw this. So we just have some generic vector, let's say. And I want to figure out that there's 3 angles that I really have accessible right away. And let's look at GeoGebra and how we can how we can work with this. So I'm going to bring up GeoGebra here. And I'm going to put it in 3D mode. Okay. And I rotated. Notice that I always rotate when I go that. So the red is pointing out sort of to the left and down. That's the x-axis. And I'm going to use the vector command here to program I, J, and K. So I'm going to say capital I equals vector, parentheses, and now tell it the ending point. So parentheses, 1, 0, 0. And there you can see it's graphed the 3D equivalent of I. Do you see that? Right there? Okay. And now I'm going to program J in. So capital J equals vector, parentheses, the point it ends on, so parentheses, 0, 1, 0. And so I have J on my picture now. And let's program in K. Capital K equals vector, point 0, 0, 1. So I have I, J, and K programmed in there, right? Now, let's say that I'm working with a vector, some vector. I'm just going to make it up. Let's say that I'm working with the vector v equals the vector, let's do negative 1, 2, 3. Okay. Everyone see that vector there? Yeah, see that? Oh, I didn't mean 0.1. No. I didn't mean 0.1. I meant negative 1. Let me fix that. 0.1 is hardly distinguishable with 0. So that didn't look right. There we go. I meant negative 1, 2, 3. There we go. See that? So that vector's pointing somewhere above the second quadrant, if you will, right? It's sort of behind, it's not sort of, it is behind the YZ plane, if you will. Yeah? Okay. Now, it's nice to know what angles this vector makes with our coordinate system. So it makes sense to ask, well, what is the angle between this vector v that we just graphed here and let's say I? What is the vector that, the angle there? And so GeoGebra can do that quite easily. All I have to do is go up here, and one of these is angle. See, that's angle right there. Click on that. And then I just have to click on V, angle between V and I. And it goes ahead and puts it there. And I don't know if you can see that. Hopefully you can see that on the on that. that it said that that's 105.5 degrees. See that? That is the angle between I and the vector you've given me. Okay? So that's 105.5 degrees. Nice. Okay? We'll call that angle alpha. That's the angle that my vector makes with I. Okay? Let's now click on find the angle between vector v, the vector you gave me, and j. Okay? I'll turn off alpha for now. And so do you see that clearly there? The angle between j coming out at us here like this and our vector v. And it says that it's 57.69 degrees. Yeah, see that right there? Okay. 57.69 degrees there, yeah? Okay. And then there's one more angle that I could ask it. I could say, well, what's the angle that you make with the k component, with the k vector? And so I click on angle and have GeoGebra find that as well, clicking on v and then clicking on k to come up with that angle as well. These three angles form information about which direction v goes in, right? This vector goes off over there, and I have the three angles that it makes with my coordinate system, the I, the j, and the k, to demonstrate sort of to communicate what direction this vector is going in. You get some sort of visual of that, knowing the angles between that, right? Let's see now how that works. Those are the angles that we are interested in working with, what we call alpha, beta, and gamma. Alpha, beta, and gamma. Alpha is the angle with v with I, beta is v with j, and gamma is v with k. Okay, let's go ahead and write down some stuff now using that visual that we had there, right? All right, so to prepare for this, to write out what we got here, since I'm interested in the angles between like v and I, let's say first off, let's calculate the dot product, right? Because I now know that the dot product is associated with angles. And so I would like to take the dot product of v with I. Well, that certainly equals the following. The magnitude of v times the magnitude of I times the cosine of the angle between v and I, which I've already labeled alpha, the Greek letter alpha. Okay? So would you agree that that's just using the formula for dot product, using the physics formula for dot product, right? But this is awesome because I know the magnitude of I, that's unit vector, right? I is a unit vector, it's 1 unit long. And so v dot I is actually just the magnitude of v times cosine of alpha, since the magnitude of I is 1. But I can also calculate v dot I using our original definition. Would you agree that this also equals v1 times 1 plus v2 times 0 plus v3 times 0, right? Because I's components are 1, 0, 0, and V's components are v1, v2, v3. So that means, when all is said and done, v dot I is also just equal to v1 straight up, the first component of v. That means these two things have to be the same thing, right? So we end up getting that the magnitude of v times cosine of alpha is actually equal to v1, which tells me a nice formula for cosine of alpha. It's v1 divided by the magnitude of v. And we call that a direction cosine. Direction cosine. So v1 divided by the magnitude of v, this is a direction known as a direction cosine. Yeah? And this is the one, the direction cosine for just the first angle, right? The alpha, yeah? I can do now the same argument with j, and I can do the same argument with k, right? So by similar reasoning, replacing the I with the j doing that same calculation, would also get me cosine of beta equals v2 over the magnitude of v. And cosine, replacing I with k, would get me cosine of gamma equals v3 over the magnitude of v. This is what GeoGebra was calculating, by the way. It was saying, oh, I know these pieces of information. You gave me a vector v. I know its first component, and I can calculate its magnitude. And then I take an inverse cosine to figure out what that angle is. It did that like in 3 nanoseconds, and was able to provide the direction angle alpha, the direction angle beta, and the direction angle gamma. When they're solved for the cosine, we call them direction cosines. Yeah? And so that is sometimes a useful way of figuring out what direction a vector is going in, right? Now, one nice relationship that holds for the direction cosines is the following. If you play around with this a little bit more, you can start to notice something here. For instance, if I take vector v and divide it by its magnitude, right? Okay. This is equal to 1 over the magnitude of v times the vector v, which is v1i plus v2j plus v3k. Right? Now, wait a minute. If I distribute that scalar all the way through, notice what I get here, v1 divided by magnitude of v. But that is cosine of alpha. That's the I component of v divided by its magnitude. Plus v2 over magnitude of v, that's cosine of beta. J plus v3 over magnitude of v, that's cosine of gamma. K. Okay? That's what the vector divided by its magnitude is. But now wait a minute. Because the magnitude of v divided by magnitude of v, wait a minute, isn't that normalizing the vector? Remember what we were saying? This is a vector v given any vector v. Divide by its magnitude, you're guaranteed that the magnitude of that vector is 1. You're guaranteed a unit vector, which means the magnitude of this is 1, which means the magnitude of this vector over here has to also equal 1. But the magnitude of this vector over here is the following equation. Cosine squared alpha plus cosine squared beta plus cosine squared gamma has to equal the magnitude, which is 1, squared. And so we get this very interesting relationship among the direction cosines. Very much like cosine squared plus sine squared of an angle equaling 1 in trig. We get this interesting thing. The alpha, beta, and gamma, the direction angles, have this relationship. Cosine squared of alpha plus cosine squared of beta plus cosine squared of gamma has to always equal 1. Does that come up often? No, but it does. It is nice to have in the back of your mind that that relationship exists, that it's there. Yeah? Awesome. Okay. Let me finish off this video by doing another concept, another reason why dot product is super useful. Yeah? And that's talking about the projection of a vector, which is something super useful in physics, right? One of the most beautiful things, one of the most nice things about vectors at all is you can sort of break them down into their components. And then instead of looking at the vector being all complicated, you can look at its simpler components, right? Now, you're probably used to doing that for, a vector in 2 space. If I have a vector like this, if you have any experience with vectors, you've probably been asked before, what's the horizontal component, right? And what's the vertical component, right? And you've broken down a vector into its horizontal and its vertical components, right? So for instance, if I had the vector 4, 3, the horizontal component is 4 and the vertical component is 3. Yeah? Sometimes though, horizontal is not convenient, right? Sometimes horizontal is not very convenient at all. So suppose I have an inclined plane, two words that strike fear into every beginning physics student. Inclined plane, all right? So I have an inclined plane, and I have, let's say, a boat on a wheel, and I'm a terrible drawer, so you can laugh at this picture. This is going to be hilarious. Okay. There we go. We have a boat on this thing. And I don't know about you, but using my intuition on physics here, I don't need to know much about physics to understand that this will want to fall or roll down the plane, right? It's at an incline, right? If it was horizontal like that, I have the good sense, intuitive sense, this is going to stay put, right? But if I, rotate it like this, and now it makes a certain angle here, I have a feeling this is going to go down the ramp, right? Why? Why though? Why does it go down the ramp, right? And one of the answers, obvious answers, is, well, gravity, right? Gravity is affecting it, right? Well, gravity is also affecting it here, isn't it? But it's not moving when it's horizontal, right? Versus gravity affecting it a little bit differently when it is at an incline. So just saying gravity really isn't, it is because of gravity, but, sometimes it moves and sometimes it doesn't. And it depends on that angle, doesn't it? Well, one way that we can really get the idea of how much this gets affected by is the following. We know that gravity points or sort of acts towards the center of mass of the Earth, right? And for all intents and purposes on the surface of Earth, we can say that gravity points downward. That is the direction of down, towards the center of mass of the Earth, yeah? That means this has a certain force acting on it, which is the weight of the object. And I can now represent that as a vector, capital F. Its weight is a force acting straight downward, right? But because this is not allowed to move straight downward, there's a plank in the way, there's an inclined plane in the way, what I'm actually seeing is two components acting on this thing, right? And one of the most convenient ways to think about this is to break down this weight force right here into two components. I want to sort of rotate this and draw it like this. There's a component going this way against the ramp, and there's a component going this way along the ramp. Do you see that? I still have access to that right triangle. Here's the force of weight acting downward, but I've rotated it and sort of done the vertical, right? Sort of done the vertical here and the horizontal components. But wait, vertical and horizontal, right? Because really, the orientation of this picture is this way, right? And this can be picked up and moved. So I can move that here, and I see that a portion of the weight is acting in this direction. This is why it's wanting to move that way. Now there's a lot of the weight keeping it attached to the inclined plane, and that's this force here. So let's see, our book calls this, let's call this W1, and let's call this W2. So you can see that the force, the weight of the object, can be very nicely thought of in two pieces or two components. I can think of it as a component acting perpendicular to the plane, to the inclined plane, keeping it attached to the plane. It's not floating away, for instance, right? And then I can see a portion of the weight acting along the travel of the plane. And so this is why when it's this much rotated that I get some movement. But if it was this way, right, if it was a boat just sitting and chilling like this, yeah, gravity is still working on it, right? Gravity is still working on it, but because there's no incline, all of the weight is acting orthogonally, normal to the surface. And so there is no left or right movement, right? It's the same weight, but it's acting, there's none of it acting in the left or right direction. Unlike this has a strong component of weight acting in that way, and it's going to want to go that way. It's going to want to travel in that direction. Breaking these vectors down into what we call these components, super useful. In fact, I can write very plainly that f in this case is equal to w1 plus w2. That's w1 added to w2. That gets me f. And these are called the vector components of f. And you can see there's multiple choices that I could do here, right? I could say, well, no, I want to project this on a horizontal thing. Here, I projected this weight basically onto the plane, the inclined plane. And that's what I mean by that. I projected the weight, the f vector, onto this line. This made more sense to think about it as horizontal relative to the boat than did actual horizontal of the surface. See what I mean there? Now, let's get to this. How can I can actually calculate these given a pretty good formula here, right? So, given any vector you like, you can always break it down into two vectors, one that's parallel and one that's orthogonal to something. So let me write this all out. Definition. Let u and v be non-zero vectors. Okay. Also, let u equal some w1 plus w2, okay, where w1 is parallel to v, okay, and w2 is orthogonal to v. This is just like saying, hey, I can write this vector as a horizontal piece and a vertical piece, except now I don't have to have a general horizontal. I can have v, another vector, tell me what I'm measuring against versus parallel versus orthogonal. Okay, I'm going to draw a picture real soon here. But let's name these. W1 is called the projection of u, vector u, onto v. Okay? The projection of vector u onto v. That's the w1 part. Yeah? And of course, we have a shortcut notation in math. And so we will say the following: w1 equals proj, P-R-O-J, projection of u onto v. V is a little subscript on P-R-O-J. So this is read the projection of u onto v. The projection of u onto v. And if you're nervous about not seeing this, it's okay. We're going to draw a picture after this, but let me just get this definition out, and then we will make pictures and make sure that we understand what we're looking at here. W2 also has a name. It's not used very much, not in this book anyway, but sort of trivially, W2 is equal to the u that you had, that was given, and subtract W1 off. Right? I mean, literally, that's just a subtraction of this. It's a solving of this for W2. But it's called the vector component of u orthogonal to v. So W2 has a name, W1 has a name. So when I say the projection vector, I'm talking about W1. W2, I'll have to be a little bit more specific and say it's the vector component orthogonal to v. Picture time, let's do it. Okay. So here is, let's say this is v, and I'm going to intentionally draw v to not be horizontal, right? So v is sort of, angled relative to my paper like that, yeah? And let's say that u is something like this, okay? Given these two vectors, I can project u onto v. Here's how I do this. Imagine v extended on the line that it goes through, right? So if I thought of vector v as pointing this way, there is an imaginary line, right? Like that v lies on, right? Now, all I have to do is break u down into a vertical component relative to that line and a horizontal component to that line. So in fact, to draw this better, I am going to rotate my piece of paper just so I can make sort of a visual vertical here, make a 90-degree angle. Right there. See that? So I'm now going to draw two vectors. Here's vector W1. This is W1. Right? And this is vector W2. Okay? And I've done what was promised. I projected u onto v, meaning I broke u down into two components, two vectors. One vector W1 that's parallel to v. You can clearly see that it's parallel. It's just a scaling of v. And one that's orthogonal to v. Makes a 90-degree angle with that vector. See that? So we call this, we call W1 is the projection of u onto v. See that? And so that is a vector that I know is parallel to v, and it has a certain length. We'll talk about that in a second, right? We'll talk about what the actual measurement of the length is. But hopefully everyone sees, everyone in chat, okay, this is a vector. The projection vector is this here. This is the orthogonal projection, right? Or the component of u orthogonal to v. That one is less used for us, but nonetheless, it can be important. Yeah? If I have, this is for an acute angle, by the way. Let's now draw an example where it's an obtuse angle. So suppose I have vector v hanging out over here, and let's say that u is obtuse. The angle that it makes is obtuse with that. The process is literally the same. Envision the line that v is located on. Right? And now think of the vertical that it makes with that line and the horizontal that it makes with that line. And so now, doing this straight 90 degrees here, let's see. That looks good. Make that to be 90 degrees right there. Right? And now draw my vector. So this vector is going to start here and go off this way. This is W1 now. See that? And this is W2. Okay. And I did what was promised. I said, hey, look at vector u. I can break it down into two components. One that's parallel with v. Remember, parallel means that it's just a scalar multiple. It doesn't mean that they point in the same direction, right? But they are living on the same line, right? I could multiply by a negative scalar, yeah, to change the direction. So W1 is indeed parallel to V, right? And W2 by picture here is definitely orthogonal to that. And so the projection vector in this case is pointing opposite in the direction of V. But that's the projection of U onto V. It's very important also to keep the ordering correctly. In other words, the projection of V onto U is not the same as the projection of U onto V. You can't switch those and have the same thing guaranteed, right? For instance, let's go back to this picture. If I wanted to project V onto U, well, now I have to draw the line that U is on. Number one ways to screw up good pictures. Let's just draw more on it. Yeah. And so now I have to project V onto this line. So now I want to rotate and make a vertical to that line. That's going to be this right there. And so that projecting v onto u is going to be here. See that? Like that. And so that is nothing at all like W1. So the projection of v onto u is very different than the projection of u onto v. So you can't switch those very easily. And you're definitely not going to have the same vector if you do that. Okay, awesome. Now, yeah, let's get a formula for this, and I think that'll be a good place to end this video. I'm not quite done with dot product. There's yet another thing I want to do with dot product before we move on with the section, but I think we are running out of time soon. So let me get this formula down a little bit, and then we will end it there. Okay, so here's a formula for the projection. Projection using a dot product. Oh, nice. Okay. All right. What I'd like to do, right, is basically use the same picture here. Right. And I want to project. Maybe I'll do a new picture because I don't want to ruin that picture even more. Okay. So yeah, here I'll make a nice looking picture. I think. Let's do. Yeah. Okay, so here is V, and let's do U, that. Okay, and then I want to project U onto V. Okay. All right, so here is my projection vector. It goes to here. Remember, V stops right there. The projection vector, this is PROJ, projection of U onto V. So in this case, in this picture, it's actually longer than V. Yeah. I want to come up with a formula for that vector. Okay. So I need to tell you a little bit about its direction, and I need to tell you a little bit about its magnitude. Right? Then I can describe the projection vector to you. Right? That's basically what I need to do. I need to tell you the magnitude of the projection, and I need to tell you what direction it's going in. So I need two things. I need direction, and I need the magnitude. And then I'll be able to come up with a formula for that vector pretty easily. All right, so what's the direction of the projection vector? By definition, it must be parallel to V. So it goes in the direction of V, right? So the direction will be a unit vector pointing in the direction of V. So I want to use V, but divide it by the magnitude to get its direction. So now I have a unit vector pointing in the direction that I want, right? So this is the direction of the projection vector, parallel to V, and I've made sure it's unit length, so it's a true direction. Okay. Now let's get to the magnitude. This is where the dot product's going to come in, because do you see that this makes a lovely right triangle, doesn't it? The length of this side, this is the adjacent side in a right triangle here. So I know that cosine of theta has to equal the adjacent side, which is the magnitude of the projection vector of U onto V, over the magnitude of the hypotenuse. The hypotenuse is magnitude of U. See that? Right? Okay. Which means that the magnitude of the projection vector, which is what I wanted to figure out, right, is actually equal to the magnitude of U times the cosine of theta. See that? So that's the magnitude of the vector that we have there. Yeah? So the magnitude is magnitude of U times cosine of theta. Okay? So now I know that this vector, the projection vector, by formula, right, is going to be its magnitude, which is magnitude of u cosine of theta, times the direction it goes in. So there's one possible formula for the projection vector, okay? Now that's not one that we use very often because we like to get the dot product happening here. This is so close to the dot product. It's the magnitude of u times the cosine of theta. I really wish this had a magnitude of v right here. Well, let's make that true. I'm going to multiply the top and bottom by magnitude of v. So I'm going to get magnitude of u times magnitude of v times the cosine of theta divided by the magnitude of v multiplied by the vector v divided by the magnitude of v. See that? Why did I do that? Because now look at this. Our dot product showed up. This is the definition of dot product. This is u dot v. And so I end up getting this formula. U dot v upstairs divided by magnitude of v times magnitude of v. So that's squared times the vector v. Here is a nice formula for the projection vector, right here. The projection vector is u dot v divided by the magnitude of v squared. That's the number, that's the scaling you provide to vector v. You know that the projection by definition is parallel to v, and so therefore it's got to be a scalar multiple of v. What is that scalar multiple of v? It happens to be u dot v divided by the magnitude of v squared. There's yet another way that we can do this, and this will tie in another result we had earlier. What is the magnitude of v squared? That can also be thought of as a dot product of v with itself. And so here is a really nice, lovely formula for the projection vector, completely in terms of dot products. U dot v divided by v dot v happens, multiply that by v, gives you the projection vector of v onto u. Yeah? Or sorry, of u onto v, I mean. I said that the backwards way. Projecting u onto v is this formula. Take the vector you want to project and then dot it with everywhere else the vector you're projecting on. See that? And that's how you can calculate the projection vector. I got to wrap up this video. We're running out of time here. So I'm going to do more example. I'm going to do an example using that formula next time. Then we're also going to talk about another application that the dot product can give us, and that's finding the work done by a force. Yeah. And so that ends up being related to the dot product as well. So you can start to see that the dot product was not arbitrarily defined. It was defined in such a way to actually do some physical things, right, with physics. And so that's why it's a useful multiplication, and that's why it's stuck around. And yeah, so I hope that today's lesson taught you a little bit about that. And maybe even if you saw dot product before, that maybe you learned something new about it, or the way that it works or operates. And so looking forward to next time where I teach you a little bit more about the dot product, and then we'll get into cross product, the second multiplication of that. All right. So until next time, everyone, hope you're taking care of yourself, take care of each other, and until next time, be well. See you next time.
Oh, Professor, I had a question.
Sure. Hold on one sec.
Sorry about that.